Hello, and welcome to the lecture on 5.3. Today we're going to talk about trigonometric graphs. Specifically, what we're going to talk about is sine and cosine. Get right into it with this unit circle. So remember that as we rotate around the unit circle, we're going some t distance. So as t gets larger, it'll rotate farther. Right? So we keep that in mind as we move forward. Also recall, sine of t on the unit circle is equal to y, and cosine of t on the unit circle is equal to x. Meaning that when we come across a terminal point for some t value, the x-coordinate is the cosine, and the y-coordinate is the sine. I do also want to note that sine of t plus 2 pi is equal to sine t. Similar for cosine. Now, notice, this plus 2 pi, all I'm saying is that if we go this distance t, and then we go another full circle, then we land in the exact same spot. So we're actually at the same terminal point, i.e. the same y value for sine. Because remember, sine of t is equal to the y value. So sine of t plus 2 pi is going to be this exact same y value. Let's go ahead and define a few things, and then we'll get into sort of how to graph these functions. A function f is called periodic if there is a positive number p such that f of t plus p is equal to f of t for every t. What I mean by that, suppose that we have this graph here. It looks like this. Let's say that we have a t value here, t. Now, give us another distance, p. This would then be t plus p. We go out t, and then we go along this distance p. Then we have t plus p here. Notice that the y value associated with the t is the same as the y value associated with t plus p. Now, as we move this line segment of length p around, that will always be true. The y value associated with the x value on one side of the line segment will always be the same as the y value associated with the x value on the other side of the line segment. Now, what we mean here is notice how this p distance is long. It skips one of the repeated mountains here. What if instead of going from here to here, we went from here to here? Would it still be periodic with this p value? Yeah. Move up, we're still touching, we keep coming down, we're still touching everywhere, and we go back up. So this would actually be the period of this function, that small distance from here to here. That would be the period. Not the other one. The other one was twice as long. It would still mean that the function is periodic if we use the other one. But the period, the smallest p for which the graph repeats, is called the period. If f has a period p, then the graph of f on any interval with length p is called one complete period of f. So notice here, this would be one complete period. We would go up, down, and back up to where we started. Show you what I mean here. Suppose we have like a heartbeat style graph. We go over, up, down, up, over, up, down, up, over, up, down, up. Suppose that we have this style of periodic graph. Then one period, roughly this. Now, I'm not exactly perfect, so my graph might not be exact. What I mean is, if we move, with this definition, what I mean is, this length, this blue length here, is P. No matter where I am, as long as the blue length is touching the graph, it would graph one full period of what's happening. And then that period will just be repeated over and over and over again, constantly. So with this heartbeat style graph, we could plot from here to here for our interval, and that would still be one full period. We could plot from here to here, which would be also one full period. It doesn't matter where we start and end the interval. All that matters is that we graph an interval with length p, so that we get every single value that the function achieves. And we would still be graphing a full period. But we're not talking about the heartbeat graph or that little mountain graph. We're talking about sine and cosine. Periodic properties of sine and cosine. The functions sine and cosine have period 2 pi. That should make sense. It's one full circle on the unit circle. So this means then that sine of t plus 2 pi is equal to sine of t, and cosine of t plus 2 pi is equal to cosine of t. On the unit circle, what this represents is going a full circle around. So if we rotate to here as our t value, and then we go a full circle from there all the way around, this green would be just 2 pi. So we would move t, and then another 2 pi, we would end up in the same exact spot. So this should make sense that these will be periodic in this way. So next what I want to do is I want to look at what the graphs look like of these two functions. So suppose I have this unit circle here. As t rotates around, I'm going to plot many of these t values on the xy plane as a function of sine. So we have sine of t is going to be what we graph. The t-axis will be the x-axis. So as t increases, meaning that t is going around the circle, t will be increasing along the x-axis here. Okay. Now remember, sine is the y value. So we're talking about vertical distance here. So this first value will be here. We'll have a second t value, third t value, fourth, we go up to 1. Then we come back down. So let's start here with this very first one. However far I rotated t is how far I'm going to move along the x-axis. So this distance, whatever it is about this distance here. Then I'm going to use this vertical distance to get my sine value. So it will be roughly that long. Second point will be roughly this long, a little longer. Third point, be a little bit longer. Fourth, fifth. This would be right around 1. This would be at t equals pi over 2. Let's go right here. So let me mark that. And then after pi over 2, we start to come back down. And then at pi, we're going to end up being, let's do one more here. And then at pi, we're going to be here on the x-axis. This would be pi. That's when the vertical distance is 0, because remember, the vertical distance is related to sine. Then we start moving into the negative y values. So we have here, we have a negative y value, negative y value, negative y value. And then at 3 pi over 2, we get to negative 1, And then we start shrinking back down. Okay. So our first negative y value after pi is going to be right about here, about that long. And we get down to about -1. I think that's about -1. This would be 3 pi over 2. And then we start to come back down towards 0. These vertical distances start to shrink. So what this graph will look like is at t equals 0, our vertical distance is 0, so we start here at the origin. And we get this style curve. It'll look something like this. This would be our sine curve. That's just graphing the vertical distance on the unit circle. Now, my unit circle is not perfectly circled. That's why my lines are a little bit short or long, but it's okay. So now let's do the same thing, but for cosine, right? Now we're graphing the horizontal distances. This, of course, is 2 pi. Instead of graphing the vertical distances, because this sine is the vertical distance, it's the y value on the unit circle, we want to graph the x value. We're going to take horizontal distances, and we're going to use those distances to estimate the sine curve, or the cosine curve. So we have at 0, we start at 1. At the next t value, again, as we rotate around the unit circle, we're down a little bit. The next t value, as we rotate around the unit circle, down some more. And then here, at pi over 2, we actually cross the x-axis. This is where our x value is 0. This would be at pi over 2. Got to switch to red because we're going negative. So after pi over 2, we have these negative values. And then we get a -1 here at pi. And then we start shrinking again. And then at 3 pi over 2, we hit the x-axis again because we get a 0 for our x. Our horizontal distance here would be 0. And then we go back to being positive values, positive x values. We have then something like, and we reach back up to +1 here at 2 pi. We're going to end up with something that looks like this. So our cosine curve comes out to looking like this. Where we start at 1, we go all the way down to -1, and then we come back up to 1 with y values. We start at 1, our x values go down to 0, they go out to -1, and they come back to 0, and then they move back up to 1. Here. This is how we graph the sine and cosine curves to start, and then we have the general shape. And these will continue to repeat forever. Because they're periodic, we talked about periodic functions, and this is just one period of the cosine curve. This is one period of the sine curve. So because t can keep rotating around the circle, our vertical distance will increase, decrease down to 0, go negative to -1, go back to 0, and then it'll just repeat itself as we move around the circle. So we'll just keep on going up and down. This same idea here. It'll keep going. Our x distance starts at 1, it moves down to 0, goes to -1, and then it goes back to 0, and then back to 1. And then we would just start the cycle all over again as we rotate, as our t values rotate around the unit circle. Let's go ahead and graph this a little bit better. So we have pi over 2, pi, 3 pi over 2, 2 pi. For sine starts at 0. It reaches 1 at pi over 2. At pi, sine goes back down to 0. It reaches -1 at 3 pi over 2. And then at 2 pi, it reaches 0 again. So it goes something like this. Has this basic shape. Similarly, cosine has the exact same shape except it's shifted. Cosine starts at 1, and then at pi over 2, it hits 0. At pi, it reaches -1. At 3 pi over 2, goes back to 0, and then at 2 pi, goes back up to 1. We start at 1, we come down. You want to make these curves very smooth. They're not very sharp like the absolute value curve. These curves are very smooth. And this one's cosine of t. The next topic I want to talk about is graphs of transformations of sine and cosine. Note, think of sine of t and cosine t like f of t. Sine and cosine are the names of the function with input variable t. Just like in f is the name of this function and the input variable is t. What I mean to say here is that you cannot separate t from f, just like you cannot separate t from cosine or t from sine. It doesn't make any sense. Sine needs an input variable, so does cosine, and that's what this represents. Sine of t, cosine of t. Recall that c be a positive number. F of t minus c shifts the graph of f of t to the right c units. F of t plus c shifts the graph of f of t to the left c units. F of t plus c shifts the graph of f of t up c units. And f of t minus c shifts the graph of f of t down c units. So these graph shifting techniques that we've used in previous classes still apply to sine and cosine, just like they would apply to any other function. Now, as we get further in this course, we'll look at these in a little bit of a different light, but for right now with sine and cosine, this is sufficient. Now let a be greater than 1. Y equals a f of t stretches the graph of f of t vertically by a factor of a. And 1 over a f of t shrinks the graph of f of t vertically by a factor of a. F of at shrinks the graph of f of t horizontally by a factor of a. And f of 1 over at stretches the graph of f of t horizontally by a factor of a. And then the last two are the reflections. Negative f of t reflects the graph of f of t about the x-axis, and f of negative t reflects the graph of f of t about the y-axis. Let's go ahead and do an example. Now, with that recall, you should remember, hopefully, your graph shifting techniques. They all apply for sine and cosine. I'm going to graph the stretching factors vertically and then horizontally. So let's start with vertically. We graph 3 different functions. Y equals 2 cosine x. Y equals 1/2 cosine x. And y equals cosine x. Go ahead and get one full period of cosine. 3 pi over 2 pi and 3 pi over 2. Now with the 2, that means that our vertical distance is going to be stretched by a factor of 2. So y equals 2 cosine means we stretch vertically by a factor of 2. The graph y equals 2 cosine x, we start at 2 instead of 1. We still come down to 0. At pi, we reach -2, not -1. back up to 0 at 3 pi over 2, and then we go up to 2 at 2 pi. So it'll look like this. This would be this would be 2 cosine of x. Now, the black curve is just the regular cosine curve, meaning that we start at 1, not 2, because we have a 1 here. We're not stretching it vertically. Still cross at pi over 2, reach -1 at pi, still cross the x-axis at 3 pi over 2, and we reach 1 at 2 pi. It'll look like this. That's the regular cosine curve, and then the 1/2, we shrink by a factor of 2, meaning we cut all the vertical distances in half. So instead of going all the way up to 1, we only go up to 1/2. Again, cutting 0 by 2 doesn't do anything, so we still cross at pi over 2 and 3 pi over 2. But at pi, we go down to -1/2 instead of -1, and at 2 pi, we go up to +1/2. It's a lot flatter curve. Now let's go ahead and do the horizontal stretch and shrink, but we're going to use sine this time instead. We're going to do the exact same thing. Y equals sine 2x. Y equals sine x. And y equals sine 1/2 of x. Now for this one, a lot of students get confused. So what I want to do is try to explain this as best I can by using the unit circle as an aid. So we're going to go ahead and only use these points. Now I'm going to exaggerate my y scale a little bit so that we can kind of see a little bit better on how the curve, we're going to accentuate the curve a little bit more. We still have 2 pi, pi over 2, and 3 pi over 2. Now, if you remember, this will shrink the graph by a factor of 2. So instead of going all the way out to 2 pi, we're only going to go out to pi. So one full period of this graph is going to be just out to pi instead of 2 pi. And we can kind of see how this will work. So suppose that I use 0. Sine of 2 times 0 is still sine of 0. So we still start here at 0. If my t is pi over 2, though, then sine of pi over 2 times 2 is sine of pi. So we're actually going to hit 0 here as well. In order to get the maximum value, to get up to 1, we need to use pi over 4 instead. Now pi over 4 on the unit circle is right here. And remember, the y value for sine of pi over 4 is equal to root 2 over 2. Now I want to show you something here though. So if I plug in pi over 4, which is this point right here, and I plug it into this curve, I get sine of 2 times pi over 4. But sine of 2 times pi over 4 is the same thing as sine of pi over 2. So we're not even using this value. When we plug in pi over 4 for t, or for x in this case, it gets multiplied by 2, so we're actually checking the sine of pi over 2, which is here, not here. Right? And the sine of this value is 1. So we go all the way up to 1 here. Same thing happens at 3 pi over 4. At 3 pi over 4, we get a -1 instead. It would be sine 3 pi over 4 times 2. And this cancels here, and we're left with the 2 in the denominator, and we'd be looking at sine 3 pi over 2 instead. This 2 modifies your input. And because it modifies your input, we actually end up, instead of rotating to here, we end up looking at the y value here, twice as far. So we get a -1 there, and then if we plug in sine of pi, it'd be the same thing as looking at sine of 2 pi, so we get 0. So this will look a lot like this curve here. My curves are not perfect, but best I can do. Now for the middle curve, plugging in just a normal sine curve. So at 0, we hit 0. At pi over 2, we're at 1. Pi, we're at 0. 3 pi over 2, we're at -1. And 2 pi, we're at 0. So this would be what the normal sine curve looks like. That's the normal sine curve. All right, now to do sine of 1/2 x. Now this one's a bit tricky because instead of doubling our angle, we're taking 1/2. So this is actually going to stretch it by a factor of 2. It's going to double the length of the period. So we should get something that looks this long instead. One full cycle will be to here. Okay. Now, if we try plugging in pi over 2, it would be like plugging in sine of pi over 4. So sine of 1/2 times pi over 2 is the same thing as sine of pi over 4. So the y value at x equals pi over 2 is the same as the y value of sine of pi over 4. So pi over 4 is normally root 2 over 2, as we stated before. So pi over 2, we actually are only at root 2 over 2. We're down here. And we plug in sine of pi, we multiply that pi by 1/2. So I'm plugging in pi for x, so I have 1/2 times pi. This is the same thing as pi over 2. So at pi, we actually reach the 1 value. At 3 pi over 2, it would be the same thing as 3 pi over 4, the y value of sine of 3 pi over 4. And if we look at sine of 2 pi, then we're looking at sine of pi. Because sine of 2 pi times 1/2 would give us the sine of pi. So if our x value for this curve is 2 pi, then it's the same y value as sine of pi, not 2 pi. So we get a 0 here. Now at 3 pi, it'll hit -1, and at 4 pi, it'll hit +1. We actually get this curve here. Much more stretched out, like this. Hopefully that helps you with your stretching and shrinking of graphs both vertically and horizontally. I feel like shifting is pretty straightforward. We're going to do an example of that in a bit, but for right now, let's continue with the section and go on to a definition. The graphs are called the sine curves or the cosine curves. Sometimes we refer to them as sinusoidal curves. Sinusoidal curves are just sine curves or cosine curves. So they're basically the same thing, they're just shifted a little bit. But I refer to them occasionally as sinusoidal or sinusoidal in nature or something like that. Just means I'm referring to a sine curve, that's all. Let's define some parameters for the sine and cosine curve. The sine and cosine curves, y equals a sine kx and y equals a cosine kx, where k is greater than 0, have amplitude absolute value of a and period 2 pi over k. So, we haven't discussed the amplitude yet. The amplitude is actually just the height of the curve. So for this curve, for instance, the amplitude is 2. It reaches above and below its main axis 2 units. The blue curve has an amplitude of 2. The red curve has an amplitude of 1/2. It only reaches above and below its axis 1/2 of a unit. So we have an amplitude of 1/2 here. Now all of these curves have an amplitude of 1. No matter how stretched out they are, the amplitude only refers to how tall it is, how far away from its axis, the axis that it oscillates over. So here we're oscillating over the x-axis, and we move away from that axis by a unit of 1 for each of these curves. So the amplitude is 1 in this case. Now the period is a little bit different. The period on all of these is exactly what we discussed before. It's the length of the interval for one full cycle of sine or cosine. So here, one full cycle of cosine is still 2 pi. That's the normal period for sine and cosine. Here, the periods are different. One full cycle of this cosine curve is actually just pi, because it finishes the entire sine curve and then hits pi. Now for the black one, it's 2 pi because it's just a sine curve, so it goes through its entire curve on an interval length that's 2 pi. But for the red curve, it's 4 pi. This would be 3 pi and this is 4 pi. It takes us an interval length of 4 pi to get through one entire cycle of sine. That's what the period is referring to. And this is how we find it with these curves. Absolute value of A, and that should be noted here. We had an amplitude of 2, amplitude of 1/2, and then 2 pi over k. And if you look at these graphs, you'll see that if you take 2 pi divided by the number in front of x, you'll get the exact period. Let's go ahead and graph one now. Let's do an example here. Sketch the graph of y equals -2 cosine 4x. All right, so first things first, what I want to do is I want to find the period and the amplitude. Remember, amplitude is equal to the absolute value of A. In our case, A is -2. So the absolute value of -2 is 2. So our amplitude is 2. Now we have to keep this negative in mind because it reflects about the x-axis, but the amplitude is still just 2. The period is 2 pi divided by the number in front of x. So 2 pi divided by 4. That gives us a pi over 2. Go ahead and graph this. Our amplitude is 2, which means we need to move away from the axis over which we oscillate by 2 units. We're oscillating over the x-axis in this case. And then we have a -2, means we start at -2 because it's cosine. Remember, cosine always starts at a maximum. So we start at -2 instead of +2 because of this negative. I want to figure out how to draw my x tick marks. They refer to the period. So let's say that this is pi over 2. I need to draw 4 tick marks. So half of pi over 2 will be pi over 4. And then this will be pi over 8. And this is 3 pi over 8. 3 pi over 8 being the midpoint between pi over 4 and pi over 2. You can just add these two together to get this. Anyway, so we start here. We're going to hit the x-axis here, go up to 2, come back down. Now, with a lot of practice, you'll be able to do this a lot more quickly than you probably are currently able to. Usually, we just use 4 points. The 4 points would be at where it reaches its maximums and where it crosses the x-axis. So our cosine curve is going to look something like this. If you want to check, you should check to make sure that these points actually reach their maximum. So cosine of 4x, what if our x is pi over 4? Then we're looking at cosine of 4 times pi over 4, which is equal to cosine of pi. The cosine of pi is -1, but since that -1 is being multiplied by a -2, we get a +2. That's where I got this point. At 3 pi over 8 and pi over 8, if you plug in pi over 8, you're actually taking the cosine of pi over 2, which is 0. And if you plug in 3 pi over 8, you're taking the cosine of 3 pi over 2, which is also 0. That's where I got these 2 points. And then here and here would be the 0 point. Obviously, plug in 0, you get cosine of 0 is 1. 1 times -2 is -2. If you plug in pi over 2, then you have cosine of 2 pi. And cosine of 2 pi is 1. 1 times -2 is -2. That's where I got this point. I would recommend trying to stretch and compress your graph using the techniques that we've had before. Try one on the accompanying worksheet. Find the amplitude and period, then sketch the graph of y equals -3 sine 1/2 x. Shifted sine and cosine. The sine and cosine curves y equals a sine a x minus b, and y equals a cosine a times x minus b, where k is greater than 0. Have amplitude absolute value of a, period 2 pi over k, and horizontal shift b. Now this should all make sense from the techniques that we learned in previous classes where we shift a graph or stretch and shrink. These should all make sense. We're affecting x directly, therefore we shift horizontally, b units. If b is positive, we would have x minus a number, a positive number, means that we shift to the right. If we have x minus a negative number, we shift to the left. Now, this k, this is an important part, so be careful here. This k needs to be factored out of the x minus whatever. So this is your horizontal shift, but only if your k is factored out. If your k is not factored out, then you're going to get the wrong horizontal shift. You have to be careful with that. You'll get the correct period, but you'll have the wrong horizontal shift. I'm going to show you what I mean here with this next example. Find the amplitude, period, and horizontal shift, then sketch. Our function is y equals 3 sine 1/2 x plus pi over 4. Then we need to figure out what these are. So let's do these first. Figure out the amplitude, period, and horizontal shift. So amplitude will be absolute value of 3. Our a is in front of the sine. That's 3. Amplitude is absolute value of 3. So we get 3. Our period is 2 pi over k. Now our k is in front of the x. So we'd have 2 pi divided by 1/2, which is 4 pi. So our period is going to be 4 pi. It's going to take 4 pi units in order to go 1 full cycle of sine. Now our horizontal shift, we have to be careful. Note that our horizontal shift is not pi over 4. Notice that the 1/2 is not factored out like the k is here. Notice that the k would distribute to both the x and the b. Here, the 1/2 is just multiplying by the x. What you want to do first is factor out this 1/2. So 3 sine 1/2 x plus pi over 2. Notice how this changed from pi over 4 to pi over 2. Our horizontal shift is pi over 2 to the left. Or just negative pi over 2 if you prefer that nomenclature. Anyway, my point is that you need to make sure this 1/2 is factored out. If it's not factored out, you need to factor it out. So we're going to take our normal sine curve. We're going to stretch it vertically by a factor of 3. Stretch it horizontally by a factor of 2. So we get a period of 4 pi. And then we shift everything pi over 2 units to the left. So first, what I'm going to do in red is I'm going to graph 3 sine 1/2 x. And then I'll shift it after. Okay. Let's go ahead and do our period, just 4 pi. So this is 4 pi. This will be what marks the end of my first cycle. Halfway between is 2 pi. Halfway between, pi. And then between 2 pi and 4 pi is 3 pi. So these are my tick marks. Now I also know that I am stretching vertically by a factor of 3. I need to do 3 tick marks above and below on the y-axis. And sine starts at 0, so we start here at the origin. First tick mark is our high point, second tick mark is at 0, third tick mark is our low point, and fourth tick mark is 0. So this is the graph of 3 sine 1/2 x. Now what I need to do is shift all of these points pi/2 to the left. So I'm going to draw new tick marks here, 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 and here. This would be pi/2, 3 pi/2, 5 pi/2, 7 pi/2. And this will be negative pi/2. So all of my points will shift to the left pi/2 units. And here to here. So I have a point here. This point shifts to the left. This point shifts to the left. This point shifts to the left. And this point shifts to the left. So my actual graph, y equals 3 sine 1/2 x plus pi/2, will look like this. So the final graph is in blue. The intermediate graph before I do my actual shifting is in red. Try one on the accompanying worksheet. Extrapolate from this example to include a vertical shift. Find the amplitude, the period, the horizontal shift, and the vertical shift. Then sketch the graph. If your function is y is equal to 2 cosine 1/2 x minus pi minus 2. Right. So you need to notice that this is your vertical shift. Your horizontal shift, your 1/2 is already factored out, so this will be your horizontal shift as well. All right, that's going to be it for today. I will see you all in the next lecture.